What's up, physics? It's Miss Bailey here again with another sweet note video, this time about Newton's first law. This will be the first of a few laws that you will learn this unit in physics, talking about that guy Newton. So now that you can see it's me, I'm gonna hide my face. Bye-bye, face. And now we're just gonna talk about this law that you've probably heard of before. In some form or fashion, it said the same thing that you see on the screen, or something very similar. An object in motion continues that same motion, or an object at rest stays at rest unless acted upon by an unbalanced force. Even I try to say the other phrase that is really popular. So all the other versions you've heard of this are probably correct. There might be some weird versions that I don't like, but they're for the most part saying the same thing. The phrases that I kind of want you to keep in mind, I'm going to highlight. So an object in motion continues that same motion. So basically, this first little part, an object in motion continues that motion, or an object at rest stays at rest, basically is saying an object is going to keep doing whatever it's doing. So if it's sitting there, it's going to continue to sit there. If it's moving at a constant speed, it's going to keep moving at that constant speed until something causes it to change. That change is caused by that unbalanced force you see here. Okay, so the best examples I can think of, I've either demonstrated in class, or you can just imagine. Let's say you're playing soccer, or better yet, I like to use mildly abusive examples. So here is a person. We can say it's me. Woohoo, there's me. I'm at rest. I'm standing there. And I am going to keep on standing there until something happens. Maybe Mr. Horstmeyer comes along. I don't know if any of you have me in class. He likes to kick or pretend to kick me. So I would be standing there until he would do that. That would be a perfect example of first law. I am staying there until some unbalanced force acts on me, causing me to change. The reverse is true. If I'm moving, or maybe Mr. Horstmeyer's moving and he's walking down the hallway nonchalantly, he's going to keep doing that until I trip him or do something else that'll cause him to change his motion. You get the idea. This law is also known as the law of inertia, which I will go on to explain what inertia is. But I have a dumb little trick for you to remember. There are 3 different laws we are going to learn this unit, Newton's first, second, and third laws of motion, and only one of them is known as the law of inertia. My trick: which of these numbers looks the most like the letter I for inertia? That would be this one, number 1. The first law is the law of inertia. Just a dumb trick for you to help you remember what that is, but it will make more sense once you relearn what inertia is, because I know a lot of you have heard of it before. So what exactly is inertia? The definition is down here. It is how much resistance to change an object has. So I want you to think for a second about objects that are really hard to change, or maybe a better way to think of it, or to be more specific about it, which objects are really hard to move, or which objects are really hard to slow down to a stop. My favorite example is an 18-wheeler. When I'm driving, I get really nervous when I drive next to 18-wheelers, and that is because if we were to collide, nothing would happen to the 18-wheeler, but everything would happen to me. So what's the difference? A lot of you would say the size or the mass is the difference between me versus an 18-wheeler on the road. The 18-wheeler would definitely win if we collided because it is much more massive. It is harder to change that 18-wheeler's motion or shape or location or anything compared to my small car. I drive a little Subaru. It's cute, but it'd be easy to move compared to the 18-wheeler. So inertia depends on mass. The more massive I am, like with this 18-wheeler, the more inertia or resistance to change I have. So, is it easier to throw a pillow or a car battery? Definitely the pillow, because the pillow, a lot of you would say, is lighter. It's less massive, it's less resistant to change. I give the example, I had filing cabinets in one corner of my room that I eventually moved to the other side of my room Way over here. What is something I did before I moved those filing cabinets to make it easier on myself? Well, I emptied those filing cabinets of their drawers and just made it to where it was lighter and therefore easier to change because I can only produce so much force. So I need to do what I can to make it less resistant to change. So just remember, inertia is resistance to change. It's the reason why most objects do what they do. That's why it's the first law. And we have a joke in physics. If you ever don't know the answer, inertia is probably a good guess. Now, that doesn't mean that's the answer for everything. Like if I toss something up in the air and it comes back down to the ground and I ask you why it does that, the answer is clearly gravity, so don't guess inertia. But if you're lost, a good guess is inertia. I also like to compare it to maybe you've driven in a car before where someone slammed on their brakes. When that happens, what happens to you? You kind of lurch forward. That's because you are still moving at the speed you were moving at before the car applied a change, before the car slammed on the brakes. You wanted to keep doing what you were doing before. You were resistant to that change because of your inertia. So again, all objects, think about stupid analogy, but think of how much change stinks for people. Nobody likes change, right? Whenever you're pushed outside your comfort zone, it's kind of that same idea. Everybody's resistant to change. Everybody's not used to the unfamiliar. You want to keep things the way they are. That is kind of nature's way. Still happens. We still proceed forward, but natural resistance is there. Great. Here's a meme before memes were really memes and super popular, but this truck clearly had an incident with the big block it was carrying. It somehow ended up in the back of the truck. My guess as to what happened is the truck was proceeding forward and it slammed on the brakes. So accelerating or applying a force in the opposite direction. That huge, massive block had inertia and wanted to continue forward, even though the truck was kind of accelerating in the opposite direction. It looks like it wasn't fastened down, and it even looks like the top and possibly the bottom were very smooth. So very little friction for that brick to grip itself inside that cargo hold. So inertia happened, and it kept doing what it was doing, whatever speed it was. That truck did not stop gradually enough. I'm sure they're fine. All right, you have this worksheet embedded in your notes, and I'm going to kind of just walk through the answers with you. And then good news, this video is over. So I'm going to zoom in so maybe we can read this a little better. An astronaut in outer space is away from gravity and friction when she throws a rock, or in this case, a baseball. What will the rock do? Well, since it's away from gravity and away from friction, there are no forces acting on that rock after it leaves the person's hand. Sure, there's an applied force to get it going, but after it's going, there's no other forces acting on it. So that rock will continue moving until it encounters a force that will slow it down or change its direction or do something to change it. The rock's tendency to keep doing what it's doing is called inertia. Great. Number 3. The sketch to the right shows a top view of a rock being whirled clockwise at the end of the string. So this is whirling this direction. If the string were to break at the indicated position, which direction would that rock fly? It's kind of easier if you try this on your own, but at each point in the motion, the rock or whatever you're whirling will be traveling a certain direction. It's constantly changing direction as it's moving in a circle. But if that thing that's causing it to change its direction, the string in this case, is removed, it will proceed in the direction it's traveling at that particular moment. So I would say C would be my answer here. It would keep doing what it's doing at that moment because any force causing it to change is gone. All right, last little bit. Zippy Doodah is standing in the aisle of a bus that travels along a straight road at 100 kilometers per hour. He holds a pencil as shown. Relative to the bus, the pencil is moving. It's not moving, 0 kilometers per hour. So if you're on the bus, you see him just holding the pencil. It doesn't look like it's moving. But in reality, the person, the bus, and the pencil are all moving at 100 kilometers per hour. So relative to the road or people standing on the road, if you want to think of it like that, the pencil has a horizontal velocity that is the same as the bus. It's moving with the bus. So imagine you're a person on the road watching this happen. You're not moving on the bus, so you see something else. Zippy releases the pencil, so he drops it, falls down. Relative to the road, the pencil still has that horizontal velocity of 100 kilometers per hour. Because of inertia, it's resistant to change. Unless something specifically causes it to change, it's going to keep doing what it's doing. This means that the pencil will strike the floor in front of his feet below his hand. It will fall the same as if he were on a non-moving object, which is the answer to the next question, is the same as if the bus were at rest. They are all moving together, so you really wouldn't see a difference. I like to compare this to if any of you have been on an airplane and you've poured a soda. That airplane is moving pretty fast, so why doesn't the soda splash all over you as you're pouring it? Well, that's because you're all moving at the same speed. The same way that all of us are moving on Earth all of the time. We're all rotating at the same speed, so we're never really at rest. But because we're all moving together, we don't see the motion. We just see us all, the differences between us. And there are no differences, or there are differences, but there's no difference in the way we're moving around the Earth, except when we travel. So how does this demonstrate the law of inertia? You can put whatever you want here, but the pencil will keep moving with that same horizontal velocity as the bus until something causes it to stop. Cool. There is math associated with not really inertia, but with mass and finding mass and weight. You can look forward to watching another video.